Right now, while you are hearing these words, something is happening that almost nobody on Earth knows about. A machine, no larger than a compact car, is moving through a region where no human spacecraft was ever expected to remain alive. It is not orbiting a planet. It is not approaching a moon. It is not even inside the protective bubble created by the sun. It was built before personal computers became common, before the World Wide Web, before most of the engineers currently listening to it were born. It is more than 20 billion kilometers from Earth. At that distance, a radio signal takes more than 18 hours to travel one way. And according to the fictional scenario you are about to hear, that machine has detected something that should not be possible. Not an alien message, not a hidden planet, not a new comet. Something quieter, something buried inside the background of interstellar space itself. The researchers in this fictional account are not using words like interesting or unexpected. They are using words like contradictory, impossible, and perhaps most unsettling of all, repeatable. This is the story of Voyager 2. And here is the part the headlines are not telling you. It is not simply what Voyager found. It is what the finding would imply about the space surrounding Earth. It is what is happening to the spacecraft right now, with only a fraction of its original power remaining. And it is what may happen in the 2030s, when the last instrument finally goes silent. Stay with me, because by the time this is over, you may never think about empty space the same way. The real story begins in the 1960s. A young aerospace engineer named Gary Flandreau was working at NASA's Jet Propulsion Laboratory. He had been assigned a task that sounded almost routine: study possible trajectories to the outer planets. At the time, reaching Jupiter was already difficult. Reaching Saturn was harder. Uranus and Neptune seemed almost unreachable within a normal human career. Then Flandreau noticed something extraordinary. During the late 1970s, Jupiter, Saturn, Uranus, and Neptune would align in a rare geometric arrangement. Not a perfect straight line, something more useful. Each planet could bend a spacecraft's path and add speed. The spacecraft could steal a tiny amount of orbital energy from one planet, then use that energy to reach the next. It was called a gravity assist. The alignment occurred only about once every 176 years. Miss it, and the next comparable opportunity would not arrive until long after everyone planning the mission was gone. NASA approved 2 spacecraft, Voyager 1 and Voyager 2. Voyager 2 launched first, on August 20th, 1977. It carried cameras, particle detectors, magnetic field instruments, plasma sensors, and a large dish antenna. It also carried the Golden Record, a collection of sounds, images, music, and greetings from Earth. But the machine was not launched as a message in a bottle. It was launched as a working scientific instrument. Its first destination was Jupiter, then Saturn, then Uranus, then Neptune. The planetary mission was supposed to be the main event. Everything after Neptune was considered an extension, a bonus. Yet, in this fictional scenario, the bonus becomes the most consequential part of the entire mission. 4 numbers matter from this point forward. 1977, 20 billion kilometers, 18 hours, and less than 300 watts. A launch year, a distance, a signal delay, and a shrinking power budget. Those 4 numbers will define everything that follows. Voyager 2 was not designed with a conventional battery that could simply be recharged. It carries 3 radioisotope thermoelectric generators. Inside them, plutonium-238 produces heat as it decays. Thermocouples convert part of that heat into electricity. The process is simple in principle. Radioactive atoms release energy. That energy becomes heat. The heat creates a temperature difference. The temperature difference produces electrical power. There are no spinning turbines, no solar panels, no fuel tank being emptied in the normal sense. But the power still declines. Plutonium decays. The thermocouples degrade. Year by year, the spacecraft receives less electricity. At launch, the generators produced roughly 470 watts. That was already less than many desktop computers use today. Decades later, the available electrical power fell below 300 watts. That power must run heaters, computers, transmitters, scientific instruments, and the systems that keep the spacecraft pointed toward Earth. Think of it this way. Voyager 2 is trying to operate a laboratory, a radio station, a navigation system, and a survival heater using roughly the power consumed by a few household light bulbs. Every watt matters. Engineers have gradually switched off heaters and instruments. They have accepted colder temperatures. They have redistributed power. They have made the spacecraft survive by asking old components to do things their designers never guaranteed. 1977. 20 billion kilometers. 18 hours. Less than 300 watts. The machine should not still be useful, yet it is. In 2018, the real Voyager 2 crossed the heliopause. That boundary is often described as the edge of the solar system. That description is convenient, but incomplete. The Sun still dominates the gravity of objects far beyond Voyager. The Oort cloud may extend tens of thousands of astronomical units away. Voyager has not left the Sun's gravitational domain. What it left was the heliosphere. The heliosphere is a vast bubble created by the solar wind. The solar wind is a stream of charged particles flowing outward from the Sun. Near Earth, those particles move at hundreds of kilometers per second. As they travel outward, they eventually collide with the material between the stars. The solar wind slows, it compresses, its pressure drops. At the heliopause, the outward pressure of the Sun's plasma meets the pressure of the interstellar medium. The boundary is not a solid wall. It is more like the meeting zone between two invisible oceans. On one side, particles from the Sun dominate. On the other, particles from the galaxy dominate. Voyager 2 crossed that boundary on November 5, 2018. Its instruments measured changes in plasma density, cosmic rays, and magnetic conditions. The real data showed that the boundary was more complicated than a simple clean shell. But our fictional story begins several years later. It begins with a pattern that should have disappeared after the crossing. Instead, it became stronger. In this fictional account, the first anomaly appears inside data from Voyager 2's plasma wave instrument. The instrument does not listen to sound in the ordinary sense. Space is too empty to carry normal sound waves over long distances. Instead, the instrument detects oscillations in charged particles. You can think of it as measuring how an invisible sea of electrons vibrates. The frequency of those vibrations reveals the density of the plasma. More electrons produce one frequency. Fewer electrons produce another. Researchers expect the density to change. Interstellar space is not perfectly uniform. It contains clouds, shock waves, magnetic structures, material influenced by nearby stars. But the fictional anomaly is different. The instrument detects a repeating sequence, a rise, a pause, a smaller rise, then a return to the original level. The sequence repeats every 17 hours, 46 minutes, and 12 seconds. Not approximately, exactly, within the limits of the aging instrument. At first, the team assumes a spacecraft problem, a heater cycle, a clock error, a transmitter interaction, an electronic echo. That is the sensible explanation. Old machines produce strange data. Voyager 2 has spent nearly half a century exposed to radiation, cold, and mechanical stress. But when engineers compare the pattern against every active subsystem, nothing matches. The spacecraft is not switching anything on at that interval. Its orientation is not changing. Its transmitter is stable. Its internal clock is not generating the effect. Then the team checks the direction. The pattern is not coming from inside Voyager. It is coming from the plasma surrounding it. This matters because plasma does not normally arrange itself into a clock. A cloud may drift, a shock may pass, a magnetic field may oscillate. But a precise, repeating structure requires a source or a mechanism, and in this fictional scenario, no known mechanism fits. Before the team can investigate, the distance creates a problem. Voyager 2 is more than 20 billion kilometers away. Light moves at nearly 300,000 kilometers per second. Even at that speed, a command takes more than 18 hours to reach the spacecraft. The reply takes more than 18 hours to return. One question requires at least a day and a half. Send a command on Monday morning. Voyager receives it on Tuesday. The confirmation may not return until Wednesday, and that assumes the command works. There is no repair mission, no replacement part, no technician with a toolkit. The nearest human being is more than 20 billion kilometers away. The signal reaching Earth is extraordinarily weak. Voyager's transmitter operates at roughly the power of a refrigerator light bulb. By the time the signal reaches Earth, it is spread across an enormous sphere. NASA's Deep Space Network must isolate that whisper from the noise produced by planets, stars, spacecraft, satellites, electronics, and Earth's own atmosphere. The data rate is measured in bits per second, not megabits, not kilobits, bits. A modern phone can transfer more data in a second than Voyager may return in many hours. So the team cannot simply request everything. Each observation must be selected. Each command must justify its power cost. Each byte must matter. 1977, 20 billion kilometers, 18 hours. Less than 300 watts. The mystery is not simply difficult to explain, it is difficult to observe at all. The first test is straightforward. If the signal comes from a fixed source far away, the pattern should remain stable as Voyager moves. If it comes from a local structure, the timing should shift. Voyager 2 travels at roughly 15 kilometers per second relative to the Sun. That is more than 50,000 kilometers per hour. Fast enough to cross a large country in minutes, slow compared with light, but fast enough to move through local plasma structures. The researchers wait. The interval changes, not randomly. It shortens by a tiny, predictable amount. That means Voyager is approaching the source of the pattern. The spacecraft is not simply hearing a distant oscillation. It is moving through a structure. Imagine driving toward evenly spaced ridges in a road. The faster you approach them, the more frequently the tires strike each ridge. Voyager appears to be encountering invisible ridges in interstellar plasma, but the ridges are not physically dense enough to behave like ordinary waves. They are narrow, regular, and aligned almost perpendicular to Voyager's path. The fictional team models them as sheets. Each sheet may be millions of kilometers wide, yet only a few thousand kilometers thick. That sounds enormous. In interstellar space, it is razor thin. A sheet thousands of kilometers thick inside a structure millions of kilometers across is comparable to a piece of paper stretched across a football field. The problem is stability. Plasma sheets should disperse. Particles move. Magnetic fields twist. Thermal pressure smooths sharp boundaries. Yet these sheets appear evenly spaced. Researchers still cannot fully explain what holds them together. The second finding comes from the magnetometer. A magnetometer measures the strength and direction of magnetic fields. Voyager's magnetometer sits on a boom extended away from the spacecraft. That distance reduces interference from the machine's own electronics. When a plasma wave passes, the magnetic field often changes with it. Charged particles and magnetic fields are connected. Move one, and the other usually responds. But in the fictional data, the plasma density rises, while the magnetic field direction remains almost perfectly fixed. That is the contradiction. The plasma behaves as though something compresses it. The field behaves as though nothing touches it. Picture squeezing a sponge, without bending or moving the fibers inside it. The water density changes, the structure does not. That is not how ordinary magnetized plasma should behave. The team checks the instrument. They compare measurements from different orientations. They account for temperature. They examine decades of calibration records. The result remains. Density changes. Field direction does not. One possibility is that the sheets are not being compressed. Perhaps particles are appearing inside them. But particles do not simply appear. Matter must come from somewhere. Another possibility is that the sheets contain particles moving in a way the instrument cannot fully resolve. Yet the required distribution would be extremely unusual. The finding does not prove new physics. One aging spacecraft cannot overturn established science, but it creates a narrow problem. Either the environment is doing something unexpected, or the instrument is producing an error that mimics a coherent external structure. Both explanations remain difficult. The third finding makes the fictional anomaly harder to dismiss. Voyager 2's particle detectors measure energetic particles moving through space. These include cosmic rays. Cosmic rays are atomic nuclei and other particles accelerated to very high speeds. Some come from the Sun, others come from supernova remnants and violent events across the galaxy. The plasma sheets should affect those particles. A magnetic structure can redirect them. A shock can accelerate them. A dense region can scatter them. But the fictional data show something else. Inside each sheet, the number of low-energy particles increases. The high-energy cosmic ray count remains almost unchanged. In plain language, the structure sorts particles by energy. Slow particles respond. Fast particles pass through. That part is not impossible by itself. Magnetic fields often affect particles differently depending on their energy. The impossible part is the precision. The cutoff occurs at nearly the same energy in every sheet. The sheets behave like repeated filters manufactured to the same specification. Nature can produce repeating structures. Saturn's rings contain waves. Planetary magnetospheres contain radiation belts. Solar plasma contains magnetic loops. But those systems have obvious organizing forces: gravity, rotation, a nearby planet, a strong magnetic source. Voyager is in interstellar space. There is no known planet nearby, no detected star, no strong local object, no visible structure massive enough to impose the pattern. The nearest plausible stellar sources are light years away. A light year is nearly 9.5 trillion kilometers. Voyager has traveled for almost half a century and has not covered even one full light day from the Sun. That comparison matters. Human technology has crossed the heliopause. It has barely entered the distance scale between stars. Yet there, almost immediately beyond the Sun's protective bubble, the fictional spacecraft finds an ordered structure with no obvious architect. There is an obvious question. What does Voyager 1 detect? Voyager 1 entered interstellar space before Voyager 2. It travels in a different direction. If the sheets surround the heliosphere, both spacecraft should encounter something similar. They do not. In the fictional scenario, Voyager 1 records ordinary density variations. No 17-hour pattern. No evenly spaced sheets. No sharp low-energy cutoff. This narrows the possibilities. The structure is not a universal property of interstellar space. It is not a simple instrumental effect shared by both spacecraft. And it is not a global pulse coming from the Sun. Voyager 1 and Voyager 2 are separated by billions of kilometers. They left the planetary region along different paths. Think of two boats departing the same island in different directions. One enters calm, open water. The other finds a field of perfectly spaced waves. The difference means the structure is local. It exists along Voyager 2's route. But local does not mean small. Based on how long the signal persists, the fictional team estimates that Voyager has been crossing the region for months. At 15 kilometers per second, months of travel correspond to hundreds of millions of kilometers. That is several times the distance between Earth and the Sun. The structure is not a single ripple. It is a region, a corridor, a layered volume of interstellar plasma larger than the inner solar system. Yet no telescope sees it. That is not surprising. The plasma is extremely thin. Even a region spanning hundreds of millions of kilometers may contain far less matter than a laboratory vacuum chamber on Earth. It is huge in size and almost empty in substance. The scale is difficult to hold in your mind. An invisible structure larger than planetary orbits, containing so little material that you could fly through it without feeling anything, and still organized enough to produce a repeating signal. The fifth finding changes the direction of the mystery. The team combines timing data with Voyager's known velocity. They calculate the orientation of the plasma sheets. The sheets are not aligned with the galactic magnetic field. They are not aligned with Voyager's path. They are not aligned with the nearest star. They point roughly back toward the heliosphere, toward the Sun. That creates a disturbing possibility. Perhaps the structure was created by the solar system itself. The heliosphere is not a perfect sphere. As the Sun moves through the galaxy, its protective bubble interacts with interstellar material. Older models often imagined a comet-like shape, a rounded front and a long tail. Newer models suggest something more complex, possibly two broad lobes, possibly a turbulent wake, possibly a structure shaped by the solar magnetic field, charge exchange, and surrounding plasma. In the fictional account, Voyager 2 may have entered a fossil wake, a trail left by the Sun's motion through the galaxy. But a wake should be turbulent. It should mix. It should fade. It should not create perfectly spaced, long-lived sheets. Researchers test whether the Sun's 27-day rotation could produce the pattern. The timing does not match. They test the roughly 11-year solar cycle. Again, the spacing does not match. They test historical solar eruptions. No known sequence explains it. The sheets point back toward the Sun, but the Sun does not appear capable of generating them in their observed form. This is where the word impossible enters the fictional story. Not because physics has been broken, because every ordinary explanation solves one part of the data and fails another. This finding would not only concern distant interstellar space, it would concern the environment surrounding Earth. The heliosphere shields the planets from part of the galactic cosmic ray population. It does not block everything, but it changes what reaches the inner solar system. Cosmic rays can affect spacecraft electronics. They contribute to radiation exposure for astronauts. They interact with planetary atmospheres. Some researchers have studied whether long-term changes in the Sun's galactic environment could influence radiation conditions around Earth. The fictional plasma sheets raise a new question. What happens if the solar system moves through one of these structures? The Sun travels around the center of the Milky Way at hundreds of kilometers per second. Over thousands of years, the heliosphere encounters different interstellar environments, dense clouds, thin regions, different magnetic conditions. If the sheets are stationary relative to the surrounding interstellar medium, the solar system itself may eventually cross them. That does not mean catastrophe. There is no evidence in this fictional scenario that the sheets are dangerous. The density increase is still tiny by Earth standards. You would not see a wall in the sky. You would not feel an impact. But the boundary of the heliosphere could change. The flow of low-energy particles could change. The radiation environment beyond Earth's magnetic field could change. For satellites and astronauts, even a small change matters. The key word is not danger, it is uncertainty. A structure that cannot be explained cannot be confidently modeled. And a structure that cannot be modeled cannot be dismissed with precision. That is what makes the finding personal, not an immediate threat, a gap in the map surrounding the only inhabited planet we know. The fictional mission team has few options. Voyager 2 cannot turn freely without risk. Its antenna must remain pointed toward Earth. Its power budget cannot support every instrument at once. Its commands take more than 18 hours to arrive. So the team uses the simplest experiment available. They wait for Voyager to cross more sheets. They compare each one: density, duration, particle energy, magnetic field direction, temperature, spacing. The sheets remain similar, not identical, but too consistent to be random. Then the interval begins to increase. Voyager is no longer approaching the sheets at the same angle. Either the structure bends, or the spacecraft is nearing an edge. The team models both cases. A flat stack of sheets cannot fit the full timing history. A curved structure fits better. The sheets may be nested, like layers of an onion. But the center of curvature is not the Sun. It lies somewhere behind and below Voyager's trajectory. There is no known object at that location. No cataloged star close enough. No planet massive enough. No detectable source of radiation. The center is empty, at least according to every available observation. The fictional researchers consider a magnetic knot, a region where interstellar magnetic fields fold around an old disturbance. Perhaps a supernova shock passed through hundreds of thousands of years ago. Perhaps the structure is a remnant, but models suggest such a feature should broaden and lose its regularity. The sheets remain narrow. The spacing remains ordered. The explanation remains close to impossible. Voyager 2 cannot investigate forever. Its power continues to fall. Engineers may keep some instruments operating into the 2030s. No exact final date is guaranteed. A component could fail earlier. Careful power management could extend operations longer. But eventually, the available electricity will become insufficient. One instrument will shut down, then another. The transmitter may continue for a time. Then the carrier signal itself will disappear. When that happens, Voyager 2 will not stop. There is nothing in interstellar space to stop it. It will continue moving, past the structure, past the reach of the deep space network, past the useful lifetime of every system aboard it. In tens of thousands of years, it will pass closer to other stars. Not close enough to enter orbit, not close enough to be captured. It will simply continue. A silent object launched in 1977, more than 20 billion kilometers away. Its messages taking more than 18 hours to reach Earth. Its remaining power measured in hundreds of watts, then tens, then none. The fictional mystery may outlive the spacecraft. Perhaps a future probe will travel in the same direction. Perhaps telescopes will learn to detect the plasma structure remotely. Perhaps the sheets will turn out to be a rare but ordinary feature. A magnetic fossil. A remnant shock. A behavior predicted by equations we already know, but have never observed at this scale. Or perhaps Voyager 2 will be the only machine to cross them for generations. So what does all of this add up to? Not proof of aliens. Not proof that physics is wrong. Not proof that NASA is hiding a secret. It adds up to something quieter. One old spacecraft, reaching a place where our models become thin. Voyager 2 was built to visit planets. Instead, in this fictional scenario, it becomes a sensor inside the space between stars. One machine, launched in 1977, more than 20 billion kilometers away, more than 18 hours from the nearest command. surviving on less than 300 watts. Those numbers are not signs of power. They are signs of limitation. And limitation is what makes the measurement matter. You do not need a dramatic claim to make the universe strange. You only need one repeatable pattern where no pattern should exist. One instrument still working after its warranty has become meaningless. And one unanswered question, moving farther away every second. When Voyager 2 goes quiet, the spacecraft will continue. But the answer may go quiet with it, at least for a generation. Subscribe and turn on notifications for more space documentaries grounded in real scientific ideas rather than exaggerated headlines. And remember, this episode was a speculative science fiction scenario inspired by the real Voyager 2 mission. The real spacecraft is already extraordinary. It does not need a fake discovery to prove that.